Next up, we're going to deep dive into the long-term metrics for planet scale commerce with Filip. Come on up, Filip.
All right, thank you. So I hope you're all not like asleep after the lunch session. I want to talk about kind of kickstart the second part by talking about how we store, basically retain metrics and query them over longer periods of time. Just briefly about myself, my name is Filip. That's my happy face when I'm not on call. That's how I look. I've been at Shopify for about 2.5 years now. Also involved in open source projects. I'm a Prometheus contributor, and I help maintain the Thanos project, which is a project that kind of helps scale Prometheus in a cloud native environment. So I want to kind of start off by defining what we mean by long-term storage. As Sam and Andre explained earlier today, the way that we ingest metrics data is we have agents that run in clusters. Those agents scrape targets. They use the remote write protocol to send metrics data to components that we call the receivers. And these receiver components retain or have a buffer of about 6 hours. This particular buffer is what we use for alerting. We kick off a lot of SLO calculation there. And also when there's an active incident, that's kind of the data that we use. Not that there's some limitation, but it's, when there's an incident, people are mostly interested in what's going on right now. And so beyond these 6 hours, data gets uploaded to cloud storage, and everything that's in cloud storage is considered long-term data, basically. And so if we can kind of alert on just 6 hours of data, and if we can troubleshoot incidents on such a short period of time, do we really need to retain data for any longer than that? There are various use cases that we need to support beyond 6 hours. For example, just the basic use case is people want to be able to monitor their service or see how the service performed over the past weeks or several months, for example. We have dashboards that are used for quarterly reporting. So people need several months of data for the dashboards. And throughout the year, there are various important events for us, such as scale tests, merchant flash sales, the Black Friday weekend, for example. We want to preserve those metrics so that the SRE team, for example, can do capacity planning for future events. Also, to give you some concrete numbers, this is the Observe Investigate tool. This is concretely Trace Analytics. What I did here is I ran a query over the past 7 days, as you can see in the top right corner, and I grouped all PromQL query instances or all PromQL query evaluations by the range across they were executed. And just here, we see that within the last week, we've had more than 1,000 queries that were executed on a range that's about 60 days or 2 months. Just goes to show that there's absolutely a need to retain data for longer. And of course, the question is then, what is a sensible retention period? Is that a few weeks, a few months, a few years? Should all of this data be retained forever? Can we delete some of it after a while? And finally, how much of the data should be queryable on demand? So do we need to have all of the data in some hot storage? Can we have it in cold storage and index it later on as users demand it? We've kind of answered those questions differently as we've developed the system, and we'll kind of see where we've arrived today. So I kind of want to start at the beginning of time, which for Observe is just 2 years ago, because Observe is still a baby. When we started off, after we did the migration, we had a very simple setup. So as we were ingesting and filling up this buffer, data was uploaded to cloud storage. We use Google Cloud, so for us, that's GCS, basically GCS buckets. And the format that was used in these receiver components is the Prometheus storage format. That's the same format in which data is uploaded to Google Cloud. And so in this bucket, the retention that we had was about 1 year. And in order to query data from the bucket, we had to run a component called a store gateway. The store gateway is able to kind of act as a proxy between query components and cloud storage and expose relevant data for a query to queryers. So then when a query had to execute a query, it would go to receivers, it would talk to the store gateway component. That store gateway component would basically return relevant data for a query, and the query would execute the query on the kind of joint data set. And so due to kind of costs, we were only able to run, to kind of load data for about a month. So even though we had data for a year, we could only load data for about a month and expose it via dashboards. Later on, we kind of extended that period a bit. So as the system was getting adoption, we set up a new set of stores which loads the data for up to 3 months. We wanted to have kind of separate deployments, mostly for resilience purposes. We didn't want a query over 3 months to kind of interfere with queries that were run from a previous day, for example. And finally, users would also come to us and ask for data from, let's say, Black Friday weekend or a particular scale test. And for that, we had to kind of provision another store gateway that would then be connected to the querier. We would follow up with the team, ask them to notify us when they were done with running queries, and then we would decommission the resources. Right, so the system that we had worked. Kind of got us over a certain hump, but we knew that we could never kind of load the full retention period because of kind of how coupled the store gateways were to data that was in object storage. So to kind of understand why that's the case, I just wanted to briefly explain how this Prometheus storage format looks like. So on a very high level, in a particular file, we have what's called an index, and we also have separate chunk files. So this index contains things like label names and label values, and querying this index requires a lot of random read operations. So the format is not particularly friendly to being queried from object storage. And the store gateway kind of, when it boots, it has to download parts of this index file on local disk so that it can amortize some of those reads. So what happens is we end up with like very direct coupling between storage and compute. So as the data set grows, we basically have to spin up more and more compute instances to extend the queryable period. And so to kind of make things even worse, these store gateways are actually not the same. Each store gateway has to load a particular shard of the data. And so when a store gateway goes away, basically we end up with an incomplete view of the data set. So if a store gateway crashes, we basically cannot trust query results anymore. Right, so in summary, we ended with a lot of resource fragmentation. It's very hard to scale the system. It's very costly to extend the retention period. When a store gateway crashes, it ends up being very slow to recover. And when we kind of looked at what other projects do in the open source community, they all kind of rely on using the Prometheus storage format in the cloud. They have some implementation of a store gateway. So we knew that we couldn't really kind of use an additional tool that was available. All right, my hand hurts a bit. So what happened now, Sonal?
Yeah, you just gotta hit the... Yeah, thanks, bro.
All right, so what we ideally wanted to have is kind of a single resource pool that would cover the whole retention period over a year or maybe above a year. That would have allowed us a fast auto-scaling path, query path, so we could add compute resources when query load would go up. We only wanted to use object storage as the only storage medium, so we didn't want to rely on local disks for caching, for example, or use some Redis cache, for example, and things like that. And the most ambitious goal that we had was we wanted querying old data to be as fast as querying recent data. So we didn't want there to be a distinction in query performance when a user would query data from a year ago versus querying data from yesterday, for example. Right, so with kind of these goals in mind, we knew that we had to go back to the drawing board, or rather the research board. And while doing research, we kind of rediscovered this format that is not really new. It's kind of been out there for more than 10 years, came out of the Hadoop ecosystem, used a lot in the Spark project and so on. So namely, the Parquet format is a columnar format that's used for a lot of analytics use cases. Also, we kind of saw that a lot of projects in the observability space use Parquet to store observability signals. So Tempo, for example, uses it to store trace data. Parka, which is a profiling tool and kind of a tool that we took a lot of inspiration from, stores profiles in Parquet files. And what's also interesting is that the Parquet spec basically defines a set of standard compression and encoding schemes. So technically, if you write a Parquet file, many different tools can later read that file. So ClickHouse, for example, can read Parquet files. DuckDB, Google BigQuery can also work with Parquet. And so that kind of gave us this idea that we would not be, or that we could later on use a different tool to analyze the data that we have stored. Right, so the way that we can think of a Parquet file basically as a table. And if we have this data set on the left-hand side, which is basically a metric with 3 labels, the way that we would represent that metric in Parquet is we can create a separate column for each label. For us specifically, we then apply dictionary encoding to each column, and then each column gets its own separate dictionary. So here, for example, the monitoring string gets encoded as an integer 1, Cube's namespace gets encoded as integer 2, and then when we apply compression, that data gets like super small. And then looking at the file format on disk, the format being columnar, every column gets written out, or the values of each column get written out separately, one after another, and then each column gets written one after another. So if we were writing this to a file, we would first write the dictionary for this first column and the values for the first column. Then where we end, we continue with the second column, third column, fourth column. And finally, we have something called a footer. This footer basically just contains some basic information, such as the location of each column and so on. So if we were to then execute this particular query, if we wanted to sum the number of pods in the monitoring namespace, what we would have to do, so here with the red, I've marked out the sections of the file that we have to read. So we read the footer, which helps us identify the locations of each column. We need to read the namespace column because we need to apply a filter. And then finally, once we apply the filter, we read the relevant samples for those time series. So with just 3 read operations, we can get all the relevant data that we need. If we compare this to a row-oriented approach where we write out one series after another instead of one label after another, we end up with a lot of read operations, which is kind of the challenge that we have with the Prometheus storage format. So knowing that we can kind of read a lot of data with a low amount of I/O. What we've kind of done and what we run today in production is the following setup. We still kind of write data to these receiver components. Those components still upload Prometheus blocks to a bucket. We now have a translator which takes those Prometheus blocks, flips them into Parquet files. And since there are a lot of Parquet files, we run a component called a compactor. The only purpose of this component is to basically take a bunch of small files and join them into big ones. And finally, we have queryers that can now read Parquet files directly from object storage. So we don't have any limits on retention. We can go back in time as much as we want. We don't need to we've kind of broken this link between storage and compute. So compute is completely decoupled, and any querier can query any Parquet file at any point in time. And finally, the component that's missing from that diagram is what we call a catalog. We tried really hard not to make this yet another service. So the catalog is just a set of files that's found in the same bucket with those Parquet files. It's less than 100 megabytes in size, so the catalog is very fast to download, and just it has some basic metadata like for each individual metric, what are the relevant Parquet files that need to be read and so on. So when a querier boots, it's going to read the catalog files. That takes less than 3 or 4 seconds, and at that point, it's basically ready to go. The last graph that I have is this chart, which shows the amount of CPU that this system has used since its inception. So this chart goes back in time 180 days, so half a year. And what it shows is that even though data has grown over time, or the amount of data that we have and we can query has grown over time, the amount of CPU that we use is pretty much the same. We also see kind of spikes in CPU. Those spikes happen on a daily basis. And so those spikes basically correspond to the auto-scaling that we do daily. Typically, when users from North America wake up, we get higher query load, and then when they go offline, basically we decommission some of those resources. I'm looking at you, Sam. All right. That's kind of the summary. I also have a small demo. I wanted to do a live demo, but Sonal wouldn't allow it. So I recorded something in my hotel room. What I recorded, or what we're kind of quote-unquote going to do. So I ran a querier on my local laptop against the staging bucket. And then I kind of executed the query across multiple points in time, and just wanted to show you what that experience looks like. All right, so cool. This is me just starting the querier. It basically takes a few seconds, downloads the catalog file. Now we can open the UI, execute the query for the 6th of this month. The query is very simple. We're just going to count the number of nodes in each cluster, and then run that for a day, for example. So that's going to take about 2.5 seconds. Given my local latency, local connection, I think that's fine. Then we're going to go back to August. That query works just fine as well. We're going to go back to February now, I think. Right, that's going to kind of execute pretty much with the same latency. Going to go back to 2023. The latency there is going to be pretty much the same. And finally, I think the earliest date that we have is 2022, November. And then we're going to run the query and get back a result in less than 2 seconds. Right, so that's all I had. Thank you for your attention, and I think we have some time for questions now. Elijah.
Cool. You talked about being able to query the Parquet I think in the Courier,
Sorry, can you repeat that again?
you talked about being able to query the Parquet data from the Courier.
Yeah, that's correct.
Is that something that you added to Courier directly? Is that open source? What does that look like?
That's a project that we kind of developed internally. We had to start from scratch. There wasn't anything that couldn't execute PromQL against Parquet files, and this is basically a project that we developed internally. It's not open source. Whether it's going to be open source is not up to me, basically.
What metric types are still challenging to query?
So what's less challenging, I would say, is high cardinality data, because since we read only columns that are relevant for a query, we can skip a lot of high cardinality columns. Those columns that users don't typically group by high cardinality. What is challenging, I don't know, actually. There aren't that many metric types. I think native histograms can be a big challenge because of how dense they are, but that would be a challenge against the old system as well.
Did this impact costs at all?
Yeah, I think we were able to shave off about 200 nodes, because again, we can auto scale on daily basis. That saves a lot of money, and we don't need to have idle compute lying around. So pretty much most of the compute that we run is used in some capacity for queries.
So you mentioned we still do the horizontal compaction. Do we also still do vertical compact?
Yeah, we do one pass of vertical compaction for deduplication. So data that's ingested in receivers is replicated. So we need to deduplicate the data the first time, basically during the translation process. From there on, we only do horizontal compaction.
And in previous versions of compactors, scaling those is difficult. Can you talk briefly about how we scale the compaction so that it's not a bottleneck?
Right. So the way we basically partition the data set into what we call metric groups. Each metric ends up in its own group bundled with other metrics, and we have, I think, about 500 of those groups. So a compactor is then able to compact a group independently. And so in the worst case, we could run 500 independent compactors. I think that right now we have like 3 or 4, and the whole process is pretty fast. All right.